let's say the alternative hypothesis, we're going to use an alternative population mean of 3.699. Now remember, that is the exact critical mean from a few slides ago. So how's that going to look? Well, it's going to fall on the distribution right smack in the middle of our alternative. Because remember, we're aligning these two distributions on that x bar of 3.699. Since we chose the alternative population mean to be 3.699, it will align right with the median of that distribution. So right down the middle. Now, of course, what this means is that our probability of type 2 error is 0.5 and our test power is 0.5. So 50-50 right down the middle. So what we can say is that when our alternative population aligns with the critical value in the hypothesized population, the probability of type 2 error and the power are both 0.5. Now, if we have a mean at point A, again, we will fail to reject the null hypothesis, and that will be correct. If we get a mean at B, we will reject the null hypothesis, but do so incorrectly. That's type 1 error. Now, if we assume the upper population is the true mean, if we get a point at D, or a mean at D, we, of course, would reject our null hypothesis, and we would do so correctly. Of course, that's the power of the test. Now, if we get a mean at C, we would fail to reject the null hypothesis because it aligns with that blue area, but we should have because it's actually part of this higher population, and that's our type 2 error. So remember, just to reiterate, the type 2 error is when we fail to reject the null hypothesis when we should have, because that mean is actually part of in this case, a population with a higher mean. Now let's take an alternative population mean that's closer to 3. So in this case, 3.10. And hopefully you can begin to think in your mind what's going to happen here. So as our alternative mean moves towards our hypothesized mean, the probability of type 2 error approaches 1 minus alpha. So for this problem, it will approach 1 minus 0.01, which is 0.99. So we'll go ahead and align these on our critical mean. And when we do so, we see that it lines up right about here. Now, of course, we need to find the z value in the upper distribution. So we find that the exact same way. So I'm going to use 3.7 instead of 3.699. I ain't going to make much difference. So 3.7, which is our mean there, minus 3.1, which is our mu sub a, divided by our same standard error we've been using, and that gives us a z-score of 2. So that is 2 standard errors above 3.10. Now we just find the area in both parts of that distribution. So in this case, our beta is 0.972, which is of course our probability of type 2 error. Therefore, the power of this test is 0.028, so about 3%. So can you see what's happening here? As the alternative population mean gets closer and closer into alignment with the hypothesized population mean, the probability of type 2 error approaches its limit of 1 minus whatever our alpha level is. So in this case, the type 2 error probability is 97%, and the power is only 3%, because our two population means are so close together. It's going to be hard to differentiate those two populations. Now, if we get a sample mean where A is, we would fail to reject the null hypothesis correctly because it's in the non-rejection region. If we get a mean where B is, we would reject the null hypothesis, but we would do so incorrectly because it is just beyond the critical value in our population mean of 3, and we expect to get one of those about every 100 times. Now, if we have a sample mean where D is, we would reject the null hypothesis, and we would do so correctly. It's far beyond our non-rejection region. And if we got a point where C is, this is the big thing here. What would happen? Well, we would fail to reject the null hypothesis because of that huge overlap between those two populations. But again, we would do so incorrectly because that point C actually belongs in this upper distribution. So that's the risk we're taking when our populations overlap so much. The rate of type 2 error greatly increases. So as our alternative population mean moves away from the hypothesized population mean, the type 2 error probability approaches 0. Therefore, the power, which is 1 minus beta, approaches 1. So now the opposite thing is happening. So let's assume a alternative population mean of 4.75, which is much higher than a hypothesized population mean of 3. Now we have to align these on our critical mean of 3.699. Now we're going to find the z-value where that overlaps, and that is a z of negative 3.50. So that is way, way down in that distribution. But we have to find the area and the probability anyway. So in this case, the beta is 0.001, and the power of the statistical test is 0.999. So you can see what happened when that alternative population mean moved way above the hypothesized population mean, which in this case was 3, versus the alternative of 4.75. Our beta, which is approaching 0, it will never reach 0, but it approaches 0, and our power approaches 1, even though it can never reach exactly 1. So beta 0.001, power 1 minus beta, so in this case 0.999. Now again, if we have point A, we would fail to reject the null hypothesis correctly. If we have point B, we would reject the null hypothesis but do so incorrectly. If we get point D, we would reject the null hypothesis but do so correctly, and again, that's the power of the test. If we got a mean at point C, we would fail to reject the null hypothesis, and of course that would be incorrect because that point belongs to the population on top. So we would fail to reject the null incorrectly, and again, that is type 2 error. Now in this case, that would happen maybe 1 out of 1,000 times, and that's the point of the power of a statistical test. It's not very likely, but it is a possibility. Okay, so let's do some curve manipulation so you can see exactly how this process is working. So let's start with the example where our hypothesized population mean and our alternative population mean are in exact alignment. So they're exactly lined up. Now the critical values will match because the curves themselves are in alignment. So the beta will be 0.99 and the power will be 0.01. Same thing as the alpha level, and of course the same thing as the non-rejection region. Because they are in exact alignment, everything lines up exactly. Now we'll create a chart over here on the right that we'll continue to fill in as we go. So where the z-critical was 2.33, the power is 0.01. Now what we're going to do is we're going to slide this top distribution over to the right every 0.5 standard errors. So we'll slide it over to 2, then we'll slide it to 1.5, we'll slide it to 1, and so forth. So the top distribution will continue to go to the right. Okay, so let's slide it over to 2. Now what do we got to find? We got to find the area in the curve on the top. So when we do that, we find the area on the left-hand side, our type 2 error probability is 0.98. Therefore, our power is 0.02. So we'll go ahead and put our power over there in the right-hand side. Now we'll slide it over to 1.5. So we'll go ahead and find these areas. So 0.93 and 0.07. So we'll go ahead and put the power of 0.07 over in our chart on the right. Now we'll slide it over to 1. Now the area in the left side is 0.84, in the right 0.16. So our type 2 error rate is 0.84 and our power is 0.16. So we'll go ahead and put that over there on the right hand side. Now we'll slide it over even further to 0.5, a z of 0.5. Now the probability on the left is 0.69. Now the power is 0.31. So we'll go ahead and put that in our chart on the right. We'll slide it over all the way to a z of 0. We already know this one. It's 0.5 and 0.5. So we put that on our chart. Now we'll slide it all the way over to negative 0.5. So the probabilities now just become the opposite of where they were before, on the other side of 0. So here type 2 error is 0.31. The power is 0.69. Then we'll slide it all the way over to negative 1. So the type 2 error rate is 0.16. The power is 0.84. So you see what's happening here. The type 2 error rate is decreasing, and the power is increasing because, again, they are complements of each other. Now we'll slide it all the way over to negative 1.5 z. So now the type 2 error rate is 0.07 or 7%, and the power is 0.93. So we go ahead and put that in our chart. Now we'll slide it all the way over to a z of negative 2. So our beta is 0.02, and our power is 0.98. Now we'll slide it all the way over to negative 2.5 z. And there our beta is 0.01, and our power is 0.99. And finally, we'll slide it all the way over to negative 3. So our beta is 0.001, and our power is 0.999. So how can we interpret this in terms of our hypothesis? As our alternative population mean, so mu sub a, moves further away from our hypothesized mean, if we reject the null hypothesis, we are almost assured that that rejection is correct. So let's say we get a bunch of sample means, like that. Now, what we can say is that if our sample mean is one of the green stars, we will, of course, reject our null hypothesis because they are not near the blue down here in the lower left. So we would reject our null hypothesis and it would be correct. But maybe 1 out of every 1,000 sample means, we would get a mean where the blue star is. Now, of course, in that case, we would fail to reject the null hypothesis because it overlaps with the blue area. Now, of course, that would be incorrect. It's just sort of the oddball sample mean on this top distribution that happens to be way over to the left. So in that case, we would commit a type 2 error. But as you can see, it's so infrequent. So 0.001, 1 out of 1,000 sample means approximately, that this is a very powerful statistical test because of how far the alternative population mean is above the hypothesized population mean. So, last thing here, and that is the statistical test power curve. That sounds real cool, doesn't it? All I did here was graph the chart we spent a few minutes building in the previous slides. So we have a z and then a power all the way down the chart. Now what I did is I kind of flipped it so it's easier to interpret. So what happens is on the left-hand side, this is where our upper population distribution aligns closer to the hypothesized population distribution. So when they're overlapping quite a bit. So you can see that the power of the statistical test is low. Now as the top distribution moves to the right, in this case, it will align in the left half of that distribution. The alternative population mean will get further away from the hypothesized population mean, and the statistical test will become more powerful. So this is a classic statistical test power curve, and you will see this anytime you look into the type 2 error rate. And sort of this is my point about there not being any given type 2 error. There's not just one. All the points along this curve represent type 2 error probabilities. And that's because it encompasses any point where these two distributions overlap. And that's the same way of saying any alternative population mean. Okay, so just a quick review, and I always go over this in hypothesis testing. Always start with a well-developed, clear research problem or question. No amount of fancy statistics will save a bad question. Then establish your hypotheses, both the null and the alternative. Determine the appropriate statistical test and sampling distribution. So in this case, since we knew sigma, we were using the normal standard distribution and the z-test. Choose the type 1 error rate. In this case, we chose 0.01. Then we state our decision rule based on our error rate and our statistical test. Then we gather the sample data, not before then, only at that point. Calculate our test statistics, compare that test statistics with our decision rule, and then we'll come up with our conclusion, and then make our decisions or inference or policy decisions or research conclusions based on that statistical conclusion in step 8. So there's a few reminders. There will be unique type 2 error for every value in the alternative hypothesis, which we showed as we slid that distribution on top to the right more and more. The alternative hypothesis value on which the type 2 error is based is simply a choice. In this case, we chose an alternative hypothesis value of 4, or mu equals 4. Now, as that alternative population mean moves further away from the hypothesized population mean, the type 2 error probability approaches 0. So if you remember, as we slid that top distribution further and further to the right, the slice on the left-hand side that represented our type 2 error rate became smaller and smaller and smaller, almost all the way down to 0. Therefore, the power, which is the complement of the type 2 error, approaches 1. Now, another way of saying this is that the test gets better at correctly rejecting the null hypothesis as our alternative population mean distances itself from our hypothesized population mean. So, if the alternative population mean is far away from the hypothesized, then when we reject the null hypothesis, we're almost certain, not exactly certain, but almost certain we're correct. Now, as the alternative population mean moves inward towards the hypothesized population mean, the probability of type 2 error approaches 1 minus our alpha. So in this case, it was 0.99. And remember, when the curves exactly lined up, the type 2 error rate was 0.99, because that was 1 minus our alpha. Now, when our hypothesized population mean aligns with the critical value in our hypothesized population mean, the probability of type 2 error and the power are both 0.5. So you remember, when we lined up the curves on that critical mean of 3.699, that split the top distribution in equal halves, so our power was 0.5 and our type 2 error rate was 0.5. Okay, so that wraps up a somewhat complex video on how to calculate the type 2 error. Now, I told you it was a more advanced topic than some of the things we've been doing, and that's okay. It helps us push our thinking. It helps us push our understanding to a deeper level, to a more fundamental level, so that when we look at a test or look at our data, we actually know what's going on. We're just not rotely crunching numbers and spitting out some conclusion. We want to know what's actually going on. Just a reminder, if you're watching this video because you're struggling in a class, stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, and you may have just hit a temporary rough patch. I have faith in you. Many other people around you have faith in you. So should you. Please feel free to follow me here on YouTube, on Twitter, on Google Plus or on LinkedIn. That way when I upload a video, you know about it, and it's always nice to connect with you. If you liked the video, please give it a thumbs up, share it with classmates or colleagues, or put it on a playlist. And finally, just keep in mind the fact that you're on here trying to learn, trying to improve yourself as a student or as a business person or whatever else you might be doing. That's what really matters. I firmly believe if you have the right learning process in place, the results will take care of themselves. So, thank you very much for watching, and I look forward to seeing you again next time.